To prevent moisture damage to valuable containerized cargo during a long or short ocean voyage, it's helpful to understand some basic information about the sources of moisture in a container, how the moisture cycle during a voyage can damage cargo, the role desiccants play in reducing moisture damage during a voyage, and how to choose the best desiccant to prevent or limit this moisture damage. First, we need to identify the sources for the moisture, and there are many. If the temperature at the location where the container is first loaded is hot and humid, there will be lots of humidity in the air. This is also called vaporized water or water vapor. Once the doors are closed, this hot and humid air is trapped inside the container. And while waiting to be loaded on board the ship, the inside temperature quickly goes up as the steel-paneled containers are exposed to the sun. Any moisture in the cargo, such as agricultural products, as well as moisture in wood and cardboard in the pallets and packaging, starts to evaporate out into the air inside the container as water vapor. Once underway, especially if the container is stacked on the deck of the ship, it is exposed to a cycle of warming and cooling throughout the entire voyage. Even containers below deck are affected by changes in temperature during the voyage. Let's take a closer look at what happens to this water vapor during these warming and cooling cycles. It's important to understand that while the volume of water vapor inside a container, expressed as grams per cubic meter, can increase due to evaporation when the temperature goes up, actual damage to cargo is the result of the water vapor changing from a vapor or gas state into a liquid droplet form when the temperature falls and water vapor begins to condensate. Science tells us that it's the temperature that determines the volume of water that can be suspended in the air as a vapor. Let's use the following example. We will assume that the volume of water vapor in the air in the container is 30 grams per cubic meter, a result of the hot and humid air being trapped inside when the container was loaded, and some additional moisture released into the air through evaporation from cargo or packaging material. We will assume that at the start of the voyage, the temperature is 95 degrees Fahrenheit or 35 degrees Celsius. Air's ability to suspend water as a vapor at a certain temperature is expressed as a percentage of relative humidity, or RH, with 100% RH indicating the air's maximum ability to suspend water as a vapor. How much water vapor the air can suspend at 100% RH depends on the temperature of the air. The higher the temperature, the more water vapor, in terms of grams per cubic meter, the air can suspend at 100% RH. Using the metrics from our example, the RH at the start of the voyage would be 75%, indicating that at this temperature, the air is only suspending 3/4 of the water vapor it is able to suspend at this temperature. And as long as the temperature stays the same or rises, the air can continue to suspend those 30 grams of water as a vapor, presenting no danger to the cargo at this temperature. Remember, warm air can suspend more water vapor than cooler air in terms of grams of water vapor per volume of air. However, if during the voyage the temperature begins to cool, say dropping from 95 degrees Fahrenheit, 35 degrees Celsius, to 86 degrees Fahrenheit, 30 degrees Celsius, the air's ability to suspend water as a vapor begins to decline, and this is indicated as an increase in the percentage of RH. When the air reaches its maximum capacity to suspend water as a vapor, it is said to be at 100% relative humidity, even though the amount of water vapor remains the same, which in our example is 30 grams per cubic meter. At 100% RH, also known as the dew point, the air can no longer suspend any more water as a vapor. And if the temperature continues to drop, a process called condensation takes place, in which the air begins to release water vapor in liquid form. Typically, a container is cooled from the outside, so the container walls and roof will be cooler than the air inside the container. This means that the warmer and more humid air is drawn into the thin layer of colder and drier air that covers the steel panels on the inside of the container. This will go on until the temperature of the air inside the container is the same as the steel panels. This action is called equilibrium, a physical phenomenon that will strive to even out the RH level in the air mass inside the container. A condensation event can occur anytime during the voyage, whenever the temperature changes from warm to cool. The amount of condensation depends on how much and how fast the temperature drops. A sudden drop in temperature during a rainstorm, for example, can create a rapid condensation event, when warm air that contains a lot of water vapor is quickly chilled inside the container by the rain cooling the steel panels. This event can cause the condensation process to continue for as long as 6 to 12 hours, releasing several liters of water. The container will quickly look like it's been showered down with a garden hose that drips down on the cargo. In both condensation events, the water vapor becomes visible as water droplets on the side panels and ceiling of the container and begins to interact with cargo, causing corrosion on metal, deterioration, or mold and mildew on other kinds of materials or products. When the temperature inside the container rises again, the air's ability to suspend more water vapor increases, and this is indicated by a lower RH. The condensated water vapor droplets now start to re-evaporate into water vapor, which is suspended in the air thanks to the rising temperature. The whole point of using desiccants in containers is to minimize the damage that these warming and cooling cycles, as well as rapid condensation events, can cause to cargo during a voyage. The following charts show the changing relationship between the temperature, the RH, and the amount of water vapor in the air inside a container during a voyage without desiccants in use. The amount of water suspended in the air in this example is 30 grams per cubic meter. As long as the temperature remains the same or rises, the RH, or relative humidity, will remain below 100%, preserving the air's maximum ability to suspend water as a vapor, and preventing any of the suspended water vapor from condensating as water droplets. And as long as the RH remains at or below 100%, the suspended water vapor will not condensate. When the temperature starts to cool inside a container, the RH level increases. Once the RH level reaches 100% and the temperature continues to drop, the air can no longer suspend all the water as a vapor, and some of the 30 grams of water vapor will start to condensate as water droplets, which can damage cargo. When the temperature in the container rises, the water vapor that is condensated will re-evaporate, and the amount of water vapor in the air will once again be 30 grams per cubic meter. And without desiccants, the amount of water vapor in the air in our example, 30 grams per cubic meter, remains about the same during the entire voyage, increasing the risk for daily condensation events that will gradually damage the cargo. These charts represent the relationship between temperature, RH, and water vapor in a container with the proper type and quantity of desiccants. During cooling cycles in a voyage, as the temperature drops in the container, today's modern desiccants will continually remove water vapor from the air, and those with built-in collectors also eliminate re-evaporation. The result? The RH inside the container never reaches that damaging 100% level. And the right kind of powerful desiccant will do this during the entire voyage, no matter how many cycles of warming and cooling the ship may experience during the voyage. Before reviewing the desiccant choices you have today, it's important that you understand what desiccants can and can't do. No desiccant can dry the cargo, only control the amount of water vapor inside the shipping container. No desiccant can control or alter the temperature in a container. Desiccants can only absorb airborne water vapor, so exposure to the air is necessary. When a desiccant reaches its saturation point, it cannot absorb any more water vapor. With these facts in mind, let's review the choices you have in desiccant solutions today and how each functions during the warming and cooling cycles of a voyage. One of the most widely used types of desiccant is the traditional pouch type, used for decades in containers. Shippers typically place a number of these pouches throughout the container and hope that they have estimated the correct quantity to effectively absorb water vapor during the entire voyage. The absorbent material in each pouch absorbs a certain amount of water vapor. However, when the temperature rises, the pouch, due to its design, allows some of the retained water droplets to re-evaporate back into the air. Depending on the type of absorbent medium in the pouch, it can generally never absorb more than 70 to 80% of its capacity due to this constant re-evaporation. And this inefficiency increases the cost per absorbed volume of water for this type of pouch or bag desiccant. Shippers now have another choice in desiccant technology, a line of advanced solutions from Buffers USA. Unlike traditional desiccant pouches, Buffers line of desiccants can be hung in containers or placed on top of cargo to work effectively with a variety of cargo configurations. Cargo made up of dry or moist products, as well as bulk or packaged cargo. During a voyage, these desiccants provide a number of advantages over traditional pouches during the cycles of warming and cooling. As the temperature inside the container cools, their larger surface areas, combined with the superior absorbing power of the calcium chloride medium, which turns the absorbed water vapor into brine water, draw in more water vapor than smaller pouches containing less powerful absorbent mediums. And, unlike the traditional pouch design, these advanced desiccants incorporate collectors that permanently hold the resulting brine mixture so it cannot re-evaporate back into the container when the temperature rises. Another line of Buffers desiccants consists of gel-based products. While they might simply look like larger traditional pouches, they incorporate some important differences and advantages. First, they offer a large absorption surface for faster absorption. Secondly, they contain a mixture of calcium chloride, starch, and a gelling agent that together not only aggressively absorb water vapor, but also limit re-evaporation. Finally, Buffers also offers a superior desiccant for use inside cargo packaging. To learn more about these superior and proven moisture protection solutions, contact Buffers USA.